Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're gonna take a look at BLDC or brushless DC motor. So before we get into it, you have to understand why there is a need for such a thing. So what do we want out of our motors is very high efficiency because it converts electrical energy into rotational energy. We don't want lot of watts turned into heat, waste heat basically. We want high efficiency, as high as we can get it. Induction motor, which is a 100-year-old technology, still is very efficient, so we want something higher than that. Then we also want high power density. Now this is very crucial for small objects like specifically your computer fans. When you have small motor, it still needs to produce enough torque, enough rotation, enough RPM, so it can be used directly without needing a gearbox or without needing to make the motor very large. So for these reasons we need high power density, and especially when you want to make like electric bicycles and things like that, high power density also helps you cut down on size. And it should not have any brushes or communicator. As you can see, brushes where it connects to the rotating part causes a lot of spark, wear and tear, and as you can see, the sparks that I'm showing here, it's not just it's a fire hazard, it also creates what's called EM noise. Now that may not be an issue for you, but especially audio equipments can pick that up, so electrically, and if you have something sensitive, you really don't want that. For these core components we created BLDC. So BLDC, you have to understand, it has very high power to weight ratio, as in like you can make it very small, as I'm showing you here, a PC fan, and it can still directly rotate the fan blades and still give you high enough RPM and torque, so you can actually move a lot of air, which is necessary for computer, specifically for servers. And it has no brush, so without the need of any brushes, as you can see, it's electronically controlled. All the electromagnets that you are seeing is controlled by electronics rather than there being a physical brush. There is no sparks here, so you can use it where, let's say, you are working with hydrogen or you're working with LPG, anything that is flammable, you can use this safely. And is very high efficiency. Now it can go as high as 98% efficiency. Induction motors can only go upwards of 90 to 96% efficiency, so that 2% efficiency actually piles up the longer you run it. So we got this. So how does it actually work? Now it has two core types that you have to understand. One is what we call outrunner, another is what we call inrunner. Basically the electromagnet, if it's on the outside, we call it inrunner. If electromagnet is in the inside, we call it outrunner. Basically the permanent magnet is the one that is always rotating. So where do we place the permanent motor? Like as you can see, this is a very common motor for hobbyist aircraft technologies and drones and things like that. For that reason, we want very high what we call torque, but we don't want a lot of RPM. And for drills, basically your power tools, we want very high RPM. For that reason we use in-runner motors. So in-runner and outrunner basically have the same topology, more or less. Only difference is one gives you a lot of more torque, which is outrunner's specific quality, and in-runner, which gives you a lot of RPM. So if you're using a gearbox, you might want to use in-runner, which is a case for drill, power tools, impact hammers, or things like that. And if you break down the circuitry of it, it's more or less like a three-phase AC motor. Now you might be wondering why the heck we call it a three-phase AC motor when it cannot run directly on three-phase AC. The reason is that it needs position feedback. It needs to know where the electromagnet is, where the magnet is, basically the north or south pole. Without it, it cannot trigger it. This is the crucial side effect of BLDC. Without it knowing where a magnet is, it cannot switch on or off the electromagnets. Without doing that, it will just vibrate if you do that. And the sole reason why this is even possible nowadays is because we have very advanced semiconductors, and basically chip on the system is very capable nowadays, so we can switch these electromagnets hundreds of times a second. So that's how you get very high RPMs. So there are some cons to it. It does give you a very high power to weight ratio. It does gives you very high efficiency, but there are some consequences of that. Consequences like it uses permanent magnets. Now permanent magnets are very expensive, especially high density one, and you do not want to use cheap magnets. Otherwise your energy will be just spent trying to rotate the damn thing. You want your magnet to be generally rare earth magnets, and they are, suffice to say, very expensive. Not to mention they lose their magnetism when they are in hot environments. Basically, when you are running a drill, and in that drill where the magnet is rotating, it can get as hot as 60 degrees Celsius or 70. So in those sorts of scenario, permanent magnets lose their actual magnetic power. So, and if you drop them regularly, they also lose it. So it's not very long lasting. Second, they require very complex electronics, which itself is not that big of a deal. However, because they require feedback, they need to know where the magnet is, where the electromagnet is, they become idiotically more expensive. Like, you can make a stepper motor driver without a feedback, but you cannot make something that runs this without a feedback. And when you go into high horsepower ratings, basically 50 or 100 horsepower, or like let's say 300 horsepower, you may find that induction motor actually gives you more bang for your buck. So at high horsepower range, these motors don't make that much sense. That's why you don't see a diesel locomotive using these things, because it's like literally running on variable frequency drive. Induction motor can directly do that, and you don't need feedback sensors. And permanent magnet that can handle 1000 horsepower would be a health hazard, as in, like, it will pick up every nut bolt, and while you are working on it, it's not only very expensive, it's very fragile, so you cannot drop it. Induction motors are like, starts to give it competition in high range. That's why Tesla motor car generally has induction motors. So with all that out of the way, what are the pros and what are the cons? You have to understand it still serves a very large function. Like, entire IT industry's fan run on this. Your hard drive runs on it. Your floppy drivers run on it. So IT has a very, very serious demand of these sort of things. And then we come to tool industries, basically your hammer, your drill, things of that nature, generally nowadays shifting to brushless motor. The reason for that is because if you have a brushed motor, it will only give you, let's say, 30 minutes of operational time. If you use BLDC with the same battery pack, you will get roughly 40 minutes time. So that 10 extra minute is a godsend for people who actually use these tools for their professional life. So, and low power electronic vehicles also use this. Like, as I'm showing you here, a breakdown of e-bikes. Basically, the motor is integrated in the wheel hub itself. So these are just a few places where you can easily see BLDC. Nowadays, even air conditioning are trying to give BLDC into their compressor. However, inverter circuit bypasses the need for that, so I'm not seeing a lot of use of it. So this was my presentation on BLDC. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, no worry about it, dislike it. And if you want to see something more, please leave a comment about that, and subscribe, press the bell icon, as I make video every day. And as always, thanks for watching.